Hey guys, I kind of forgot that there was this due as well. There's all of chapter 11 is due this upcoming week. I forgot to include the second part of it in my video, so I'm just gonna make one now. And I thought about it, and I was like, well, there is a lot of similarities between the sampling distribution for sample mean and for the sample proportion. But I don't know. I thought some of these might be difficult enough that we should go over some of them. The nice thing is there's a lot of similarities between proportion and this. And also one thing I want to note, you don't for a proportion you don't have to turn it into a a z-score if you don't want to. You could just do uh, if you're like proportion and your standard deviation and everything. Like if your proportion was zero point 0.7 and then your standard deviation was, I don't know, 0.016 or something, um, you can use these guys. You don't have to standardize the data. Like if you want to find the probability that some p hat is less than, uh, I don't know, point 0, let's just say point 6, I guess. You don't have to change this into a z-score if you don't want to. So you can just use norm.dist. So like when I was doing the standardize, I was just using the p as the mean and the standard deviation as your standard deviation. So just do that instead. The one thing you do have to do, you do have to find your standard deviation. So like if this is your standard deviation here, and then they give you your sample or whatever, you still have to do. Well, I don't think you have to do it for this, but you do still have to do that finding the standard deviation part. So let's pretend like this standard deviation is the one we calculated. So if we want the probability that, well, let's just undo this. Let's say you want the probability that p hat's less than 60%. That would simply be norm.dist. So you could do it this way too. With your x value is zero point 0.6, your mean, remember use your p, and then your standard deviation, that's the one you calculated, and then here. So you can do this as well. It's pretty small, but that's because our standard deviation is so small. So maybe I should do a slightly better value. Let's say 6, let's say 0.69 or 6.8 or 6.9, probably pretty good. And then we'll say standard deviation is 16. This should be a little better. Okay, so 0.69 should be really close to 50%. So see, here we go. This is you could do it like this as well. You don't have to do the turning it into a z-score and so on. I just did that because it might be a little easier possibly to see. Um, but you can do it this way because that's kind of how we're going to do it with the sample means. So to be consistent, you don't have to worry about getting z-scores here unless it asks you to. Okay, so that'll be, you can do it either way. If you watch the video and you're good with the first video I made this week and you're already good with it, don't worry about it. But if you are like, yeah, I kind of want a little more consistency, you don't have to worry about standardizing it. I mean, that's an extra step that's nice, but you don't have to have it. So I just wanted to talk about that because in our lectures, I'm probably going to show you guys. I might show both ways, but I might just show the norm.dist way, not the standardizing it into a z-score way, unless it asks for it. Okay, so this next chapter is sample mean. So the last one was, well, about proportion. Now we're looking at the mean in these sampling distributions. So let's do this first problem. You're going to notice some similarities. It's pretty much the same thing. The only difference is we're working with means, not proportions. The sample distribution birth weight of full-term newborns in the U.S. approximately normal with a mean of 7.5 pounds with a standard deviation of 1.25. What is the probability that the mean birth weight of a random sample of 100 U.S. full-term newborns is between this value and this value? Pounds. Okay. So they give us our mean, and then they give us our sample standard deviation. So now, in our sample standard, our population standard deviation. So be very careful when you're doing a sampling distribution. You have to find your sample mean and sample standard deviation. Your sample mean is easy. The sample mean, if you're given your population mean, all the means of your samples are going to be the exact same as your population mean. The only thing that's going to change is your standard deviation, and this is based on the central limit theorem. So the central limit theorem, so CLT, basically says kind of two things. So if you have these two conditions, I don't know why I just did -1 there. Okay, must be my cell must be formatted strangely. I just put in number. Okay, I don't know. I guess I'll just put text. See what happens here. Okay, there we go. Is it going to do the same thing for this? Okay, it is. Alright, so let me just do this. Format cells, go to text. So you have to have these two things. So first, you either have to have your n, so your sample size is at least 30, so greater than or equal to 30. And then the other guy, you either have to have that, or you have to have, in the problem it's supposed to say approximately normal. So if you have either of these, you can use the central limit theorem. So if you have this, then you have kind of this nice thing. You have, then sample will be normally distributed. So sample is normally distributed. So sample is normally distributed with mean equal to population mean. So that's your sample mean. So your samp mean equal to population mean, and sample standard deviation is equal to your population standard deviation. So let me put this in parentheses. Your population standard deviation divided by the square root of your n. So they'll give you your sample size, that's n, remember, that's how many individuals we're looking at here. So your square root of n, you divide by your population standard deviation, that gives you your sample standard deviation. So this only works, like you only get these two guys, and also the fact that you have a normal distribution, approximate normal distribution in your sample, only if one of these two or both of them are met. So if you have a larger sample size than 30, you're good. If you have that, you have approximate normality already, then that's good too. So that's our central limit theorem. I'm going to go ahead and copy this guy and put him over here, just in case we need to go back and look at him. Keep them over here, but over here I'm just going to use these for the numbers. Just put general, put it back in general. Okay, so here we go. So knowing that stuff, central limit theorem, now we can work on this problem. So still the same problem. So let's go ahead and write down this. Now, what I would suggest too is make sure you know what you're writing down. In this, it says that it's approximately normal. So this is the distribution of birth weight of full-term babies in the U.S. So this is our entire population we're talking about in the U.S. So mean of 7.5. So this mean that it's talking about goes with the population. So it's one of our parameters. So our mean and our standard deviation. These both under this population mean these are our parameters here, not our sample. And then they say our standard deviation for the population is 1.25. Okay, so now we need to find our sample stuff. Because remember, we're working with samples, so we have to use our sample information for this problem. So your mean sample, in this case, if they don't give you the sample mean, just always assume it's the population mean. So anytime they give you the population mean, just assume it's the sample mean as well, as long as they don't give you a sample mean, because they might give you the sample mean, but in this case they don't. They just give you the population mean. But now we need our sample standard deviation. So this guy, remember the formula, it's this, the population standard deviation divided by the square root of n. So we also need our n, before we can do that. So let me copy these two guys down, because that's kind of the most important part of a sample, is knowing how many people we looked at. So our n, or our sample size, is 100 people, so a random sample of 100. So 100 is definitely greater than or equal to 30, which is good, but also it tells us it's approximately normal, so we know we're already going to be using central limit theorem. So when we have standard deviation, you do your population standard deviation, so this guy, divided by the square root of your sample size. Your sample size is 100, and this is the sample standard deviation we're going to have to use now for the formula. So they ask us, what's the probability the birth weight of a random sample of 100 U.S. newborn babies is between 7.125 and 7.875 pounds? So our x1 and our x2, remember these are just dummy variables. I'm going to use for 7.125 and 7.875. So that's just these two values, and we want the probability that's below the two, right? So that's what we want, but first off, our trick, remember, to find the area between is do this. Probability, now we're doing x bar, because we're doing probability that a random sample mean is between these two values. So x bar is less than our 7.125, so 7.125. Okay, and then we want the probability x bar is less than, you guessed it, the second part, the 7.875. Okay, so we want to find these two probabilities. So now how do we do this again? Well, just norm.dist. We know it's a normal distribution, so we know it's going to follow the normal distribution function in Excel. So remember our x value, that's just the dummy variable for the data value. We want to find the area around or below. Right, in this case, remember Excel always finds the area to the left, so we want the area less than this value, so we're good here. Okay, so now our mean we just go with the sample mean, but of course the sample mean and the population mean are the same thing, so it doesn't matter which one you click. And now you have to go with the sample standard deviation, so that's the difference. You cannot go with the population standard deviation when you're working with a sample in this case. Okay, so there we go. So that's that is area to the left of this guy. So then I do the same thing here. So norm.dist. Okay, our x value now is our x2. Our mean is still the 7.5. Our standard deviation is still this 0.125, and it's cumulative. Oops, I accidentally entered in too many parentheses. Okay, so then this means the probability that our x bar is between 7.125, so x bar, and 7.875, the probability that's between this, make it a little larger, is simply, remember, the larger probability minus the smaller one, and this gets you your area in between. And there we go, that's it. So I would copy this over and paste it. It says it wants it to 4 decimals, and we got the same thing. Alright, so now this one right here, this isn't way too bad of a problem either. It's pretty much the same thing. This guy will be calculated the exact same way, just now you want to find the area, or area less than 200, so it's not too bad. The only part that might be difficult is this one, like maybe a little strange, so I guess I'll go over the whole thing. Okay, so the nice thing is too, is since I've been using all of this data, all I have to do is change these guys around and everything will change accordingly. So if I change like my population, so my parameters and my statistics, then these, and of course my values, I want to find the area around, these guys are all using the data values in Excel, right? They're calling upon the individual cells in Excel, so this means that I'll get these answers again for free. So let's do this. So here they say our, okay, the problem says that average weight of U.S. males, 20 years, 195.5 pounds. So our population mean is 195.5. Okay, and then our standard deviation, our population standard deviation is 47, right? Because that standard deviation goes with our population mean, which goes with our population U.S. males. So all the U.S. Males that are 20 years and older. Okay, now what is our sample? Probability. So our sample is 100 U.S. adult males. So still 100. Our mean, it's still going to be the same thing. It's going to be the 195 pounds. So 195.5, right? Okay, now you see that these things kind of freaked out. That's okay. We'll change these guys as necessary. Okay, so our x value that we want to find the area around. So see, look, right off the bat, our standard deviation is already changed based on what our standard deviation was before. Now, just because I'm going to go through it again, because repetition is good. So remember, it's our population standard deviation divided by the square root of our sample size, so the 100, and there we go, 4.7. All right, so our x value, we want to find the area around, is 200, and there we go. So this guy already found it for us, because I had him already, the function was already there, and it was built on everything here, right? So B10 would just mean, okay, I want to find the area less than 200, the x value being 200, good. Then this next part, B7 means, hey, this is your mean. Yep, this is our sample mean, and this is our sample standard deviation. So we see that we got that all for free. So you copy that and paste it in there, and we're good. Now this part right here, I don't know, might be kind of tricky. It's kind of like in the last problem, in the last homework, we had to do one of these. But here they say the sample size is n equal 100. What are the values for the following parameters? So these are all of our parameters. This is kind of like our parameter, but our sample of the parameter. So this should be following parameters and statistics, but whatever. So our mu, this is just our population mean. So we throw in our population mean of 195.5. And this guy, since they don't give us our sample mean, it's always going to be your population mean. So just throw that guy in there. That's why you see this twice. And then our standard deviation, sigma, remember this sign right here means the population standard deviation. So that was given to us, the 47 pounds. And then the sigma of x bar, this just means the sample standard deviation. So that we calculated to be 4.7, right? So you throw your 4.7 in there, and it's good. Okay, now the last question says, what is the probability that the average weight of a sample of 50 U.S. adult males is between 156 and 181? Okay, now the sample size is changing to 50, right? So let's change that to 50. And see, look at that. When I changed my sample to 50, my standard deviation changed as well. So that's kind of key. It just means that the smaller your n is, the larger the spread, the average spread will be in your, so the larger your standard deviation will be. There's not as many data values out there to kind of bring the average distance down a little bit. There are not as many values. Okay, so again here we have the x1 and we have the x2. We got to find probability the x bar is less than 156, right? Because we want to find the weight is between 156 and 181, so my x1 will be 156, and my x2 will be 181. Okay, so this is, since remember this is already given to us, we put this in correctly. Still using up all the values, so all the ones we changed, Excel made the changes in the function already. Only thing we have to do is retype the probability x bar is less than 181, right? Less than our next guy. Alright, so it's norm.dist still. Our x value now, the area we want to find the probability, the data value we want to find the probability around is this guy. And then our mean, that's our sample mean. our standard deviation, our sample standard deviation, and it's always cumulative. There we go. So the probability between the two values is simply you take your larger one. Now, the reason this guy is larger is look at this. This guy here, this E means, okay, this value here, so this 1.400178, multiply him times 10 to the negative ninth power. That means move this decimal over to the left 9 places. So really, really small. So be very careful when you're looking at these. Notice that E. This just is scientific notation. This is the same thing as 1.4 times 10 to the negative ninth power, which is a very small number, right? That would be like 0.1234567 8. That's basically this number, right? And that's exactly what we got. So really, really small number. So that one's definitely the smaller guy. So take your larger value, subtract off your smaller one, and there you go. Probability in between is about 0.0146, and that's what we got here. Okay, so that's that guy. So let's look at this one now. So here we have 3 histograms pictured below represent a population distribution and 2 sampling distributions of different sample sizes. So this means we have different sample sizes, but they're kind of following the same study. So assume that the variable is normally distributed within the population. Which of the following best represents the population mean? Okay, so remember the population mean is the average of all of the samples, of every single sample mean ever calculated. So if you take one sample of 50 out of like a huge population, you find that mean. You take a new sample of 50, calculate that mean, and another sample of 50, and so on, and you take every single sample of 50 possible until you've looked at every single person in your population. If you find the average of all of those averages, you get the population average. That's the idea behind this problem, is we're looking at 3 different studies of about 50 people, I think it says, or 3 different sample sizes. The average of these 3 should be very close, if not exactly equal to the mean. Okay, so look where the majority of our data lies, right? Remember, in a histogram, the smaller data values mean, hey, the frequency, they didn't occur as much. So the much taller bars are the ones we're looking at for our mean. So it looks like the majority of, I guess, the weight of all these frequencies is approximately close-ish to 15. So I'd say between 10 and 15. And then look at this. So the same thing here. This guy looks a little skewed to the right, but it looks like the majority is right around here. Again, it's around 15, maybe close to 13. And then here we go again. Look, all the weight is right around here between 10 and 15. So I'd probably say best bet's either 13 or 15. It's kind of hard without actually calculating it. But I would say it's definitely between your 10 and 15, close-ish to 15. So I'd say 13 is a pretty good guess. Now remember, this is just a guess. You're not supposed to know exactly what it is. You're just trying to pick the best, the mean that best represents this data. Okay, so let's see, that one shouldn't be too bad. Let's do the last problem. Yeah, this guy. Okay, suppose the first year salary of a college graduate from a business school of a certain college is normally distributed with a mean of $62,000 and $6,600. Okay, so first off, this is our this is the first, like, our mean, right? So our population mean, so 62000, $62,000, and then standard deviation is 6,600. Okay, so now here, remember what we're doing here. Suppose the first year salary of a college graduate from the business school of a certain college is normally distributed. So right off the bat, central limit theorem kicks in. Suppose a random sample of the salaries of 5 first-year graduates is observed. So our n is really small, right? It's only 5. So our n is 5. Our mean, well, it's the same thing, right? Remember, our sample mean should be the same thing. And this helps us answer our question, right? So 62,000 is our population mean and also our sample mean. So right off the bat, when you see this, it's trying to trick you. It says, what is the sampling distribution of our sample means? Well, the sampling distribution of our sample means just means what's the average of every single one of our means possible. Well, we know that once you take the average of every single mean, what are we going to get? Exactly the mean. So that this guy is just trying to trick you a little bit. It's just equal to the mean. Now it says calculate the standard deviation. Okay, well we know how to do that, right? Let me kill this, and then we can do this all this again. So remember, this is our n. This is our 62,000. So that's our mean. Our standard deviation. How do we find this again? It's the formula. You take your standard deviation and you divide by the square root of your sample size. So now it's our 5. So this $2,951 approximately. Okay, so that's our standard deviation. So that's what I would put in here, and it wants to 5 decimals. So I'll just copy this, throw it in here. 1, 2, 3, 4, 5. Ooh, maybe I should. It's rounded. Okay, it's rounded to 5 decimals. So actually, I think we're good. It should work. It shouldn't count it as wrong, I hope. But we'll see. Okay, so what is the probability the mean salary of the sample is less than 60,000? Okay. Now here, just like in the last, like I was telling you guys in the beginning, sometimes they'll ask you for the z-score. Here's a case where we need to find our z-score. So how do we find our z-score again? Well, our x value is 60,000. Make sure you have enough zeros there. So then what's our z-score of x? Well, how do we do this again? Standardize. So if you standardize this, take your x value, take your mean, and then take your sample standard deviation. So the z-score is this right here. So this should be our z-score. So negative, and it says it wants it to 5 decimal places. So it would be 67759. Oh, nope, it goes up by 1. So it'd be 1, 2, 3, 4, 5. You know what? Let's just make Excel do it for us. There's too much here. So this is how I'd make Excel do it for me. So right here, there's the increased decimal and decreased decimal. So decrease it to I think it said only 5, so 5 places. So 1, 2, 3, 4, 5. So here's my answer. Copy and paste it in exactly like that. And there you go. So see, not way too bad if you make Excel do the thinking for you. Sometimes it can be kind of annoying to do this. And then our probability that the z-score is less than z. Well, remember, if we have z-score, what should the probability of a z-score less than negative 0.67760 be? Well, it would just be equals norm dot, remember it's standardized, so z-scores we can use norm dot s dot dist, right? So let's see, it should be less than, so this means we don't have to worry about any complements. Click on your z-score and this, and there you go, about 20, around 25%-ish. So copy this guy over. Well, let's see, once it, so the probability should be 4 decimals. That's confusing. So 5 decimals for the z-score, 4 for the probability. So let's zoom this guy down to 4. Okay, so 2490. 2.2490. Okay, and there we go. So that's how you would do this problem. So yeah, maybe a little more is going on, but it's not absolutely terrible. Kind of similar to the last stuff we did. The hard part is really remembering that the standard deviation they give you is a population standard deviation, so that can sometimes screw you up. Knowing that, hey, I've got a sample here. I'm doing sampling distributions, not population distribution, so I need to find a way to find my sample standard deviation because it's not given to me. And then once you know the formula and you know how to do that stuff, the rest of these problems are pretty basic. But I hope this helps. If you have any questions, feel free to email me. But other than that, good luck with your homework.